Is it working? Cool. All right, so this morning we've got sort of 4 different parts we're going to go through. The first one is going to be sort of like general introduction to the Python scientific ecosystem, some NumPy, some AstroPy, kind of the general overview for people who might not be using Python already. And then the rest of it's going to be on more of the exploratory data analysis, like Daniela said. I'm going to do a section on I/O, or sort of like getting your data into Python. And then Daniela will do numerical summaries of data and a visual summaries of data section.
You can tell people that they can follow along.
Oh, yeah, right. OK. So show you how to do this. Oh, and for some reason, my screen is only showing you is cutting off the borders. But I'm seeing the full thing. So let me know if there's something that I'm talking about that is off the screen. I'll try to keep it centered. So if you go to yeah.
Since there's a lot of people who are probably familiar with AstroHackWeek and familiar with a lot of the stuff that you're going to talk about, I'd like to ask people who are familiar with the topic to engage with the workshop as a potential facilitator of this material, so that you could potentially teach this either at a WES workshop, at your own local seminar, at your own local institution, or at a local conference that you go to.
Yeah, that's a good point. And also, have people join the Slack channel that we set up? So I think it'd be great if people do have questions, like during the lectures, you could go on there and ask like clarifying questions. Or of course, you can also ask me or Daniela. But if it's like something that you think a lot of people will be able to answer, then other people can sit on there and answer some questions.
I have a question. What are the official hashtags for this week?
Very important. I think it's just AstroHackWeek.
There's also AskAHW for people following the live stream to ask questions, and then we can answer them on the lecture.
OK, so all the materials for the whole week actually are going to be on this AstroHackWeek 2015 repository. I'm not going to go through right now how to deal with GitHub, but if you don't know Git already, you can just click the download zip link and get the latest version. OK, so who here uses IPython or Jupyter notebooks? All right, so nearly everybody. Oh yeah, who doesn't? It's me. All right, great. I have something to tell people. All right, so this is I think a lot of people are going to be teaching out of them, so it's just good to know what you're looking at here. The notebook is let's go back to the top here. The notebook, just the simple version, is that it's a HTML front end to a normal Python session. So just to show you what IPython looks like, not in the notebook. IPython itself is just let's see, how do I make this bigger? It's just sort of an enhanced front end for Python. And the notebook is just a version of this where there's individual cells that you can execute Python code in and see the result immediately. So the important takeaway here is that everything that I'm doing in the notebook will work in a normal IPython session or a normal Python session. So if you're not familiar with notebooks, there's no there are some special magic things, but what you're seeing is just normal Python. Okay. All right, so yeah, so I kind of want to start out by orienting you with the scientific stack in Python, right? So Python itself isn't super useful to scientists if you just have Python. You kind of need all the stuff that's built on top of it. So in our case, it's like that first layer is sort of like the basic stuff that makes science possible with Python. So like NumPy is the array library that makes it possible to do fast numerics. IPython, like I said, is widely used. And there's stuff like Cython for speeding up code. And then on top of this layer, you have tools like SciPy, Matplotlib, Pandas. These all use NumPy, but add extra functionality. And then you can build on top of that and do more domain-specific stuff. So it's not on here, but like AstroPy, for example, is built on top of NumPy and SciPy. So that would sit somewhere up in those higher layers, right? So hopefully, if you're not already using Python, you hopefully had a chance to install Python through Anaconda. So this is our recommended method for installing Python. I'm not going to have time to go through that right now, but you can go to anaconda. Actually, what is it? No, not here. Huh? Continuum. All right, go to this website. You can download it. It should be pretty self-explanatory. But we're going to be dealing with a lot of Python packages that are sort of add-ons. So just to like give you an overview of how to install things with Conda, you would just do on the command line Conda install package name. For example, I already have it installed, so it doesn't do anything. If you get all of Anaconda, you're already going to have most of like NumPy, SciPy, all the standard stuff. Even AstroPy comes with it. You can also install things that are not part of the Anaconda distribution with Conda. So for example, the AstroML package you can install by specifying a channel. So this is saying go to the AstroPy channel and install AstroML. Oops, installee. All right, so I already downloaded that though. So, and then finally, there are some packages that are not part of the that don't have Conda packages built for them, but are available. So pip is sort of the backup option. So for example, Dan's corner package for doing plots, that we'll probably show you at some point, doesn't have a Conda package, but I can do pip install nodeps corner, and if that wasn't already installed, it would have got it. This nodeps option is usually good to use when you're using pip, because otherwise pip will try to like upgrade packages you already have and sort of mess with your whole system. So I always recommend doing nodeps to tell it to just install the package I'm asking for, not any dependencies. So the reason sort of illustrates why you want to use Conda is that Conda is an actual package manager that will take care of resolving dependencies optimally, whereas pip kind of doesn't really keep track of everything you need. It just will say, oh, you need that? OK, I'm going to install that and all the dependencies, regardless of whatever else is going on with your environment. All right, so that's any questions on packaging real quick? OK. All right, so because NumPy is sort of like the base layer, I'm going to do a relatively quick NumPy tutorial to start with, just because a lot of the examples that we're going to be going through are sort of NumPy based. So it helps to understand the basics here. All right, so like I said, Python by itself isn't really great at numerics. And so this is sort of the reason for NumPy's existence. And NumPy is what makes possible actually accomplishing things efficiently. So just to illustrate that, in pure Python, if you just wanted to create a really dumb function that just adds 1 to every element in a list. Let's see if I can make this bigger. You could write it something like this. All right, and then I'm going to create this list x and just time how long it takes to add 1 to every element in a list that's 1,000,000 lines long. So this is the pure Python version, no NumPy, takes 65 milliseconds. But using NumPy, you do something like this block here. Oops. And it's running about 1 millisecond. So it's, it's usually on the order of a factor of 50 to 100 or more faster. And this really makes a big difference when you're actually trying to accomplish things, right? So why is it that pure Python is so slow? This diagram is a little complicated, but I think it can be illustrative. So if you look on the right side, this is what's going on if you just use plain Python by itself. In our example, you've got a list of items, and that list is represented as separate integer objects. Okay, and in Python, each integer object is actually basically a pointer to some object that's living somewhere else in memory, right? So this list is just pointing all over the place. And what happens when you add 1 to each element in the list is that you go through, and Python will say, OK, I'm going to add 1 to this object. What kind of object is it? And it has to go look up what kind of object it is, and then it looks up how to add 1 to it. And it has to do that for every single element. So each time you're going through, you have to check the type of every element and ask, how do I add 1? And then it does it, right? With NumPy, what it basically allows you to do is just have these blocks of memory that it knows that every element in the block is a type integer, say, right? So that means you can just check the type once, and then it will say, go use the compiled code to add a number to all the elements in this array. And basically, because of the details of how CPUs work, this just ends up being so much faster. So yeah, operations in NumPy are faster because the data type can be checked once, and all the looping happens in compiled code. So the name of the game in NumPy to use it efficiently is to move as much operations out of loops and into the compiled code as possible. So you're just using these vectorized operations where you're doing operations on entire vectors or arrays at once. So just to give an example of what that looks like, so say we have 2 arrays, x and y, that represent some points in space. If we wanted to, say, calculate the distance from the origin for all these points, without NumPy, we could do something like this, or using loops, we could do something like this, where we create a empty array to hold our distances, and then we loop over the input arrays, and for each element, we do this operation where we're calculating the distance. Invalid syntax. I think this has to be first. But in NumPy, we would, instead of writing out that loop explicitly, just use implicit looping, where we calculate x squared. This will calculate the square on every element in x. Same thing with y. All these are doing implicit loops over all the elements in the array. So the NumPy version in this case is over 100 times faster. So just as an interesting aside here, how many arrays are created in this cell? This is something that I think like some people new to NumPy don't always quite realize. So actually, we're just calculating one output array, right? But in the process, these operations are creating temporary arrays. So this will create one array. You allocate the space for x squared, do that operation, creates an array. Same thing here. So that's two arrays. You do the addition operation. That creates a third temporary array. And then finally, you do square root and get the fourth array, and that gets saved as the output. Right?
So if you're giving us some really, really big pieces of data, you might get captured.
Yeah. It can be an issue, but Python will then garbage collect these temporary arrays immediately. So, and it's very good at that. So, most cases it's not an issue, and most people aren't even aware of this, or a lot of people starting out aren't really aware of this. But it's kind of like, to me, it's interesting that even though you're doing all these temporary array creations, it's still way, way faster than doing the pure Python version. Even though in the pure Python version, you're not creating huge temporary arrays. It's just that like the compiled NumPy code is so much faster.
It's inside a loop. All that garbage collection allocation can be into your attack.
Yeah. Well, it depends on what you're doing, I think, is the short answer.
In the old days of Fortran, I would have written x star x plus y star y. Is that any faster than square?
No.
You write in Fortran, you
Even modern Fortran?
The answer in Python is almost always profiling. Because in some cases, x times x is faster than x squared. Then the answer in Python is always profiling. You might be surprised. Yeah, but sometimes one is faster.
Yeah, I think small integer powers might just actually be translated to just take the square instead of calling like a pow function, but I'm not actually sure in Python. What's that? Let's see here. Oops. Extra cell. Okay. All right, so it's the same for this. All right, so yeah, so like as I said, the name of the game is vectorize everything when possible. So sometimes like you need to get a little creative to do this. So for example, if you wanted to calculate the difference between adjacent elements in some array, you could do these tricky indexing operations where you are taking all but the, actually, I've done this backwards. So this takes all but the last element and subtracts all but the first element. No, wait, did I do that wrong?
Yeah, that was the wrong way around.
Ah, I had the right way around? Damn it. You get the idea, though. Yes, now it makes sense. Okay. Yeah. So basically, oh yeah, by the way, this is actually, there's a NumPy function to do this too. But as it turns out, if you look at the source code for it, it's called ediff1d. And you can look at the source code, and it is actually just doing this exact thing right here.
There's also just NumPy diff, right?
Yeah, diff is a little different than this, though. But it does a similar thing. I think that diff applies to like any dimension, so it gives you like not a 1D output necessarily.
How did you just pull up that source code?
Good question. So this is an IPython magic thing in the notebook. And so if you do one question mark after pretty much any object or function, and execute it, it will tell you something about the signature. So this is super helpful if you don't want to go look up some documentation. If you do 2 question marks, it will pull up the source code if possible. If it's some compiled C extension, then it can't do that.
And is the signature the thing that's useful for what's below the
Is the signature?
You said the signature.
Oh yeah, sorry. The signature. The signature and the docstring together is what it shows you. The signature, I mean the calling signature, so the inputs and the keyword arguments up here. And the docstring actually explains something about what all those parameters are.
Which is one of the reasons why it'd be really good for people to make doc strings like that under their function model.
Good point. Yes. Always write docstrings. All right. So there's some interesting properties that these that functions in NumPy have. So these like array-wise functions that I've been showing you are known as universal functions, or ufuncs, in NumPy. And they have some interesting built-in stuff that you don't necessarily notice day to day. So if you call the plus operation on 2 arrays, it's actually calling an underlying NumPy function. In this case, this just add function to just add x and y. Does the same thing, right? But these ufuncs have methods that can do more things than just the plain operation itself. So for example, you can call accumulate on the add function, and it will add